Picture a silent traveler hurtling through the void of space for eons, its icy heart.
The gas coming from 3I Atlas doesn't match any known comet, warns Professor Brian Cox. NASA and the European Space Agency have seen comets erupt water, carbon dioxide, and carbon monoxide for decades. But the third interstellar object ever found just broke the rules. Its spectrum screams with 8 times more carbon dioxide than water. Barely any carbon monoxide and a flash of pure nickel vapor. Something no solar system comet has ever shown. Not even Oumuamua or Borisov looked like this. Astronomers are stunned. If this isn't comet chemistry, what else could survive a journey across the stars? Everything we thought we knew about cosmic visitors is now under threat. And what we'll uncover next could force us to rewrite the story of our own solar system. Comets are often called dirty snowballs, but their true recipe is more precise. At their core, most comets are chunks of ancient ice and dust, leftovers from the birth of the solar system. When these icy bodies approach the sun, sunlight begins to work its magic. The surface heats up and frozen gases trapped for billions of years start to vaporize. This process called outgassing creates the spectacular coma and tail that define a comet's appearance. For decades, NASA and the European Space Agency have used spectroscopy to decode what's in that glowing cloud. Imagine shining a beam of light through fog. Each molecule leaves a telltale mark, a set of lines in the spectrum. The brightest of these by far comes from water vapor. In nearly every comet studied, water dominates the coma. Carbon dioxide and carbon monoxide are present, too, but always in smaller amounts. Surveys of hundreds of solar system comets reveal a familiar pattern. Water vapor is usually the main ingredient, making up the bulk of the gases released. Carbon dioxide appears next, but rarely exceeds a third of the water's abundance. In fact, the typical carbon dioxide to water ratio falls between 0.0505 and 0.3, meaning water outnumbers carbon dioxide by at least 3 to 1. Carbon monoxide is even less common, sometimes matching carbon dioxide, sometimes barely detectable at all. The Rosetta mission to Comet 67P made this chemistry clear. Instruments on board watched as water vapor poured off the nucleus with carbon dioxide and carbon monoxide following behind. Other famous comets, Hale-Bopp, Hyakutake, even the interstellar visitor Borisov fit the same mold. Each time the numbers stack up. Water first, carbon dioxide second, carbon monoxide a distant third. This chemical fingerprint isn't just a curiosity. It sets the baseline for what astronomers expect from a comet. Whether it's from the Oort cloud, the Kuiper belt, or even drifting in from another star, deviations happen. A few comets are rich in carbon monoxide. Others might show a spike in ammonia or methane, but the core pattern holds. Water leads the dance. Carbon dioxide and carbon monoxide play supporting roles. That's the rulebook every comet so far has followed. James Webb's first spectra of 3 stunned the astronomy world. Instead of the usual dominance of water vapor, the data showed a chemical fingerprint that defies every known pattern. The carbon dioxide emission band at 4.3 microns blazed across the readings, overwhelming the faint signature of water. For every molecule of H2O, there were about 30 molecules of carbon dioxide. No solar system comet, not even the wildest outliers, comes close. Most barely reach a third as much carbon dioxide as water. Here, water is a footnote. Carbon dioxide calls the shots. Carbon monoxide, the other usual suspect, barely registers. The ratio of carbon monoxide to carbon dioxide hovers around 0.2. Again, far below what's expected for an object this active. Multiple observatories confirmed the result. SPHEREx, VLT, ALANG, and KEK all measured the same shocking numbers. The carbon dioxide is not just abundant. It's tightly packed near the nucleus, forming a dense inner coma. H2O by contrast is faint and scattered, almost lost in the noise. Then comes the metallic twist. High-resolution spectra from the Very Large Telescope revealed bright lines from atomic nickel Ni streaming off the coma. But the usual companion ion is missing. Not a single Fe line rises above the detection threshold. In every solar system comet ever studied, nickel and iron vaporize together in proportions matching meteorites and the Sun. Here, only nickel escapes. The nickel-to-iron ratio soars more than 10 times higher than any previous comet, breaking the rules of both chemistry and cosmic formation. Lab teams rush to test for errors. Pipeline calibrations, background subtractions, instrument cross-checks, all confirm the anomaly. No artifact, no glitch, just a real physical signature that refuses to fit any model. The gas pouring from 3-2 Atlas is not just rare, it's unique. The rules that have governed comet science for decades fall apart in the face of this data. If this is what interstellar chemistry looks like, the universe is stranger than anyone imagined. Orbital prediction is supposed to be a solved problem. Plug in the mass, the velocity, the Sun's gravity, and a comet's path should trace out with pinpoint precision. For decades, this model has worked. Whether for icy wanderers from the Oort cloud or interstellar visitors like Borisov, but with 3 Alas, the numbers refuse to cooperate. As soon as the discovery data hit the minor planet center, dynamicists worldwide raced to fit its orbit. Early solutions agreed this was a hyperbolic intruder inbound at more than 50 km per second with an eccentricity over 6. Observatories stacked hundreds of position measurements each with its own time stamp and error bar. In theory, these should line up predicted versus observed dot for dot. Instead, the residuals, the tiny differences between where 3-2 Atlas was supposed to be and where it actually appeared, began to drift. Not wildly, not enough to trigger alarm in the first week, but enough that the overlay never quite snapped into focus. The mean deviation per observation yet around half an arcsec, translating to several hundred kilometers at the object's distance. For a nucleus likely between 3 and 5 kilometers wide, that's more than just measurement noise. The first suspects were the usual ones, outgassing jets. When sunlight hits a comet, pockets of volatile gas burst from the surface, acting like miniature thrusters. The effect is real. Rosetta's mission to 67P showed that just 10 of the surface could spin the entire nucleus, shifting its path by measurable amounts. For 3I Atlas, though, the math doesn't add up. The CO2 jets pouring from its surface are powerful. But even at 30 times the water vapor, their total momentum falls short. Analysts ran the numbers again and again, plugging in every plausible outgassing scenario. No combination could nudge an object this massive by the observed amount. Each new observation only deepened the puzzle. The drift persisted, sometimes growing, sometimes shrinking, but never vanishing. No standard jet model could close the gap. The rulebook gravity plus outgassing suddenly looked incomplete. For the first time since interstellar objects entered the solar system, astronomers faced a mechanical inconsistency they couldn't explain away. The mystery was no longer just chemical. Now physics itself was on trial. 6 years before 3I Atlas, astronomers caught their first real glimpse of an interstellar visitor. In October 2017, telescopes locked onto an object later named 1I Oumuamua. Oumuamua. At first, it looked like a cosmic oddball. No coma, no tail, just a tumbling shard of rock or ice. But as it sped away from the Sun, something stranger happened. Its path began to drift, veering ever so slightly from the line gravity alone would dictate. The deviation was small but real. Confirmed by dozens of observatories and published in peer-reviewed journals. The usual explanation for a comet's course correction is outgassing. Jets of vapor acting like miniature thrusters. Yet, Oumuamua showed no sign of gas, no halo, nothing to suggest it was venting anything at all. The debate erupted almost overnight. Some researchers argued for invisible hydrogen ices, others for exotic physics. Avi Loeb, a Harvard astrophysicist, went further, asking whether we might be looking at engineered propulsion, a solar sail perhaps, or a fragment of alien technology. Most of the field pushed back, but the question hung in the air. What kind of object moves without leaving a trace? Then came Boros in 2001, the second interstellar object ever confirmed. Boros was different from the start. Its spectrum matched the familiar profile of solar system comets, water vapor, cyanogen, carbon monoxide. Its coma and tail followed the rulebook, and its trajectory fit gravitational models without a hitch. Borisov reassured astronomers that not every visitor from beyond would break the mold. If anything, it looked like a standard comet, just one that happened to be born around another star. Now, with 3 ILAS, the pattern grows more tangled. One object, Ulmuan Newer, defied gravity without a trace of gas. The next, Borisov, played by the rules. And now, Atlas, bigger and brighter than both, brings a new kind of puzzle, a chemical fingerprint that doesn't match any known comet, and a trajectory that refuses to be explained by the usual physics. 3 visitors, 3 different stories. If there's a common thread, it's that each arrival deepens the mystery, pushing astronomers to widen their search for answers. What else might be out there, waiting to rewrite what we think we know about the universe? The search for answers begins with the most conservative models. Some researchers argue that 3 Atlas is showing us chemistry from a planetary system unlike anything in our backyard. A world where carbon dioxide dominates and water ice is scarce. Exotic ices forged in the coldest reaches of a distant protoplanetary disk could have survived ejection and interstellar travel. If so, the comet's CO2-rich signature might be a time capsule from a star system where the rules of chemistry played out differently, where water was never king and volatile carbon compounds shaped the landscape. Others turn to the violence of space itself. In this scenario, 3I Atlas is the debris of a catastrophic collision. Imagine 2 icy bodies smashing together in the outer reaches of their home system, shattering crusts and exposing deep carbon layers. The fragments blasted free could carry rare mixtures, organometallics, carbonyls, or even nanopace metals preserved by the cold and darkness of interstellar drift. Some lab teams have tried to replicate these signatures, mixing exotic silicates and heavy carbon compounds under extreme cold. None have matched the full spectral fingerprint, but the partial echoes keep the theory alive. A third hypothesis focuses on chemical processing by cosmic radiation. Over millions of years in the void, high-energy particles and UV light can alter the surface of a comet, breaking bonds, releasing gases, and transforming the chemistry in ways we're only beginning to understand. If 3I Atlas spent eons exposed to the harshest interstellar weather, it might have developed a crust rich in volatile nickel compounds or other rare phases, explaining the nickel vapor without iron and the persistent CO2 dominance. Yet even the most advanced simulations fall short of reproducing the observed ratios. Then there's the scenario that sits at the edge of mainstream science. AVB, never shy about cosmic puzzles, asks whether the gas from 3 Atlas could be engineered. The idea isn't fantasy. Aluamia's unexplained acceleration forced astronomers to consider artificial propulsion, at least as a thought experiment. Here, the argument runs. The outgassing isn't random, but controlled. The signature of a device using CO2 as exhaust. NASA's own spokesperson weighs in. Extraordinary claims require extraordinary evidence. So far, the data show an anomaly, not a blueprint, but the debate, natural or artificial, remains open, fueling a wave of public fascination and scientific urgency. Every theory on the table faces the same reality. No lab on Earth has yet recreated what's pouring from 39 Atlas. Each new observation adds detail, but the core mystery deepens. If this is natural, it's a chemistry we've never seen. If not, the implications reach far beyond the comet's icy shell. And with every press release and expert quote, the world is left with a single unsettling question. What are we really looking at? Within days of Brian Cox's statement, the world took notice. Search trends for 3.2 Atlas exploded. Google queries leapt over 1,000 in August alone, outpacing even the peak of Oumuamua's media storm. News outlets scrambled for interviews with astronomers, while science podcasts and YouTube channels raced to break down the anomaly. The public appetite for answers was insatiable. Online petitions calling for new government funding to study interstellar objects gathered tens of thousands of signatures in a matter of weeks. Congressional staffers fielded calls about planetary defense and the possibility of alien technology. The European Space Agency press office logged more requests about Atlas than any mission since Rosetta's comet landing. Even late-night talk shows ran segments riffing on the possibility of cosmic visitors. But the curiosity isn't just about spectacle. For scientists, 3.2 Atlas is a chance to test the limits of what we know about the universe. Astrobiologists see the object as a messenger from another star system, carrying clues about the chemistry that shapes planets and maybe life across the galaxy. If the gases pouring from Atlas are truly unique, it means our solar system is just one example in a much wider cosmic experiment. The stakes reach deeper than headlines. Every major observatory with a spectrograph is now watching Atlas, and the James Webb Space Telescope is scheduled for another round of close-approach observations at perihelion on October 30, 25. Lab teams from MIT, Caltech, and Max Planck are working overtime trying to replicate the gas signatures in vacuum chambers chilled to interstellar temperatures. No one has cracked the code yet, but every failed experiment adds urgency to the search. The mystery has become a rallying point for the scientific community. Slack channels and conference calls buzz with new theories, some bold, some careful, all driven by the same question. What are we missing? Even seasoned researchers admit to a sense of awe and a little unease. If a comet from another star can break every rule we thought was universal, what else is waiting out there for the public? The story is personal. The idea that material from another world is passing through our neighborhood, leaving behind a chemical fingerprint no one can explain, sparks wonder, fear, and hope all at once. It's a reminder that the universe is still full of surprises.